This is an introduction to the Year 1, Semester 1 Physical Chemistry, Beer's Law and the Analysis of Cough Sweets practical. The aim of this practical is to determine the molar extinction coefficient of a food dye and determine the mass of it present in cough sweets. Learning objectives are to correctly use volumetric glassware to produce an accurate dilution series of a solution, to use spreadsheet software to fit a linear relationship to a set of data, and to investigate how errors combine and propagate through calculations. The practical comprises two parts. In the first, the settings of the colorimeter used to measure absorbance will be optimized, and a set of calibration data, that is, absorbance versus dye concentration, will be obtained. In the second part of the practical, a solution will be produced from the sample cough sweets and the absorbance of this solution measured. In order to interpret the results you will obtain by measuring the absorbance of the cough sweet solution, calibration data, which relates absorbance to the dye concentration, will be needed. The calibration solutions are made up by sequential dilution of a supplied stock dye solution. Before the practical, you should make sure you have viewed the sequential dilutions video, which also includes information on how to correctly use a safety bulb. The absorbance of the most concentrated of the sequential dilutions will then be measured using every filter available on the colorimeter. Again, make sure you have viewed the colorimeter video, which explains the operation of this instrument. These absorbance measurements will enable you to determine which filter should be selected for use in the remainder of the experiment. Using the selected filter, the calibration data will be obtained by measuring the absorbance of each solution of the dilution series. To make your sample solution, you will first dissolve on a hot plate stirrer a specific number of cough sweets, whose weight has been measured, in a small quantity of water. Once the cough sweets have completely dissolved and the solution has been given time to cool slightly, it will accurately be made up to 100 milliliters. Having produced the cough sweet solution, its absorbance will be measured using the same colorimeter filter that was used to measure the absorbances of the calibration solutions. Before you complete the practical, it is important that you estimate and record the relevant errors. The first set of errors that need to be estimated are the uncertainties in the volumes dispensed by all the pipettes used in the practical. Note that it is quite likely that the magnitude of the errors of different volume pipettes will also differ. For more information on how to estimate this type of error, please refer to the errors video. You may also find the figure shown is helpful. The other errors that need to be established are those associated with the measured absorbances and weighings. Once again, refer to the errors video, which contains details of how to estimate errors on digital readouts. Having obtained the experimental data, this will now need to be analysed so that you can generate meaningful conclusions. The first step is to use your calibration data to produce a calibration plot. A linear trend line can be drawn through the points and the equation for the line of best fit determined. In the equation given here, m corresponds to the gradient of the line and I its intercept. Having watched the absorbance video, you should be familiar with Beer's law. This states that the absorbance will equal the extinction coefficient multiplied by the path length and the concentration of the sample. Note that the extinction coefficient will be specific to both the dye and the wavelength used to measure the absorbance. On inspection of these two equations, it can be seen that, if the dye obeys Beer's law, then the gradient of the line of best fit will be equal to the extinction coefficient multiplied by the path length. By performing a regression analysis on the calibration data, the uncertainty in the gradient can be established, and thus the extinction coefficient, along with an associated error, may be determined. Combining the line of best fit equation and Beer's law, a relationship relating absorbance to the concentration, gradient and intercept can be established. Rearrangement of this will enable the concentration to be determined for any absorbance. This expression will be used to determine the concentration of your cough sweet sample from the absorbance you measured for it. Since all the moles of dye in the solution come from a known number of cough sweets, and since you will be able to determine the molecular weight of the dye used, it will then be possible for you to calculate the average weight of dye per cough sweet. You should note that the intercept will appear in the rearranged expression, but in fact this would be 0 if the calibration data perfectly obeyed Beer's law. The reason the intercept is included is that it will compensate for the presence of any systematic errors in the measurement system. When calculating the concentration from an absorbance using the rearranged expression, you will need to take into account the fact that there will be errors associated with both the absorbance reading and the gradient. However, it may be assumed that any error in the intercept will have negligible effect on the result, and hence the intercept uncertainty can be ignored. This concludes the introduction to the analysis of Koff-Sweets practical.